Hello, my name is Kun Li. I'm a senior research associate from Center for Photonic Devices and Sensors. Today, I'm going to present my Blue Sky talk on solid-state holographic LiDAR with a 360 field of view. Here is a content for the next 25 minutes. I will first start with the current LiDAR technologies and my proposed concept showing how it is different. Now we list a number of key components to realize the proposed concept. Experimental results are presented with the visible laser and the 905 nanometer laser for LiDAR. Design considerations are listed for automotive LiDAR. Finally, I will present the conclusions and some future works. LiDAR stands for light detection and ranging. It is a method for measuring distances by measuring the reflection of the pulsed laser light with a sensor. It's important for a number of applications. Most popularly is the automotive industry, the autonomous cars. For the car to drive itself, it needs to see what's around it in order to brake, turn at the right time. LiDAR is an important part of the ADAS and autonomous sensor system. It's predicted that in about 10 years' time, it will exceed radar and cameras. But with the current COVID situation, everything is degraded. So we're not expecting that sort of growth, but the trend is still the same. For the LiDAR to work efficiently, it has certain challenges. It needs to see quite far away, mostly beyond 100-meter range. It needs to see all 360 field of view in order to see if a car is coming from behind or from the side. It needs to see a 20-degree vertical angle in order to cover close and further distances. And needs to have good resolution so it can see something like 35 centimeter at about 100 meter away, and needs to be quick enough for the car to react. There are a number of LiDAR technologies here. We just quickly summarize them. Most popular one is called mechanical LiDAR. It has a number of lasers shooting towards a spinning mirror. The spinning mirror has several surfaces. Each surface have a different tilt angle. Because of that, the laser can be directed to different vertical location. And the reflected beam is being collected by a 2D detector. Distance can be worked out by the timing of the two pulses. A flash LiDAR is a bit like a camera flashlight. It sends a flash of a beam, but locally. It doesn't see all 360 like the mechanical LiDAR. It uses a photodiode array to see that area, very much like a camera would do. A MEMS LiDAR is a scanning technology. Often people use one-dimensional MEMS mirror, but the laser beam is shaped in a line instead of a point. So you end up with a line scanning the area that you're interested. There's another one called optical phased array. It uses antenna elements to change the phase of each pixels, and it diffracts a beam towards the desired location. All of the technology has its pros and cons. For example, mechanical LiDAR can see very far, but it costs very high to buy, and it's very bulky. It normally needs one per car. On the other hand, MEMS and flash LiDAR only see partial field of view, but it has a low cost, and you normally install quite a few in a car to see enough for autonomous driving. The optical phased array doesn't have moving parts. It's a solid state design, which is a good thing, but the loss of light can restrict the range of the system. There's another technology called frequency modulated continuous wave. So instead of pulsed laser, it uses continuous wave to to detect the distance. This technology is still under development, so it's not yet ready for the commercial world. My proposed concept uses a holographic technique. So it uses an LCoS spatial light modulator to split a laser beam into several beams, and it can control the direction, the location of the beam. It is highly efficient, and there's no moving parts. LCoS is non-mechanical. The mirrors are non-mechanical. It doesn't move. So it's no moving parts. The points array are updated every time with a new computer-generated hologram. So each time you load a different hologram, you would steer the beam into a different position. And the field of view is reconfigurable. It depends on the scenario. You can have all 360, or you can have the front only. Depends on the scenario. This talk is mainly focused on the light transmission part. So we will not talk about the detection, mainly focus on transmission. Here's a quick side view of a car. Normally, you would put the LiDAR system on top of the car, and it needs about 20-degree field of view to see something from quite close by, about 3 meters, to something as far as 100 or 200 meters. Some key components are needed for such a system. Most importantly is LCoS spatial light modulator. It has reflectivity about 70% at a green 532. Across the whole wavelength range, it remains roughly the same value. So at 905, where LiDAR is working on, it still averages about 70%. A very small amount is lost in the diffraction due to the backplane structure. Here's the backplane structure. It has a grate, which doesn't have high reflective coating in the middle. And because of that, you have some diffraction loss to the higher orders. Such a device can modulate all 2 pi of phase steps at different wavelengths. This particular device is designed for 1550 nanometer and has 256 degree level for very accurate phase modulation. Here's an example of the diagonal 45-degree diagonal grating loaded onto the active area. The active area has 1920 by 1080p pixels. Another key component is a convex mirror. So we need a convex mirror to steer the beam to different directions. There are mainly two different coatings, aluminum and gold. The gold is very effective, very efficient at 905. So at about here, it has about 95% of the reflection. This is important that you have very small loss in the whole system. Now we need a 905 laser. This is from laser components. It's a laser diode. As you can see that the beam is diverging differently in the horizontal and the vertical directions. The peak power of each pulse is about 220 watts. Pulse length is about 8 nanosecond. It has a fairly high rep rate, can go up to 25 kilohertz. So with all the necessary components, we will look at the device with a visible laser, and we will demonstrate with a 905 laser. So for the device to work efficiently, we need to look at the phase steps, how the electrical voltage result in the required phase steps. Here we load some quite basic blazed gratings. And this grating has 8 pixel pitch. This has 12 pixel pitch. As you could see from the numbers here, with the 8 pixel pitch, it needs slightly higher voltage range to achieve that. This is because that each pixels, the neighboring pixels have a very sharp flatback region. And for the sharp flatback region, it has effect on the neighboring pixel to go beyond 2 pi of phase steps. So instead, if you use normal voltage, it doesn't go up to 2 pi, so you need to overshoot it a little bit. This effect doesn't appear in the longer pitch. So you really need to optimize the voltage for the desired phase profile. The phase profile has effect on the diffraction efficiency. Here, as we can see that for different pitch, diffraction efficiency is different. With a longer pitch, a smaller diffraction angle, the diffraction efficiency is higher, but the angle is a bit small. Vice versa. This is for the vertical diffraction diffraction grating. If we look at the horizontal diffraction grating, which means the beam is steered in the vertical direction. In this way, we see an increased diffraction efficiency. This is due to the rubbing direction of liquid crystal molecules. The horizontal rubbing direction is in favor of horizontal diffraction grating direction. Hence, you see a slightly higher grating, slightly higher efficiency. After we worked out the rough efficiency we get from a simple grating, then we can use a CGH to work out, for example, here is 3x3 points array. Then we have a diffraction efficiency about 35%. This is quite different because this hologram is much more complicated than the previous grating hologram. And this is a combined version of small steering angle and large steering angle. On average, it works about to be 35%. Quite a number of the power goes to the zeroth order, and also quite a bit goes to the higher order. This is because the device is not designed for the visible. Where here we are using green wavelengths, but the device is designed for near infrared, 1550. So in order to have higher diffraction efficiency, we need a device suitable for that particular wavelength. So this is at the far field, and this is after. This picture shows the 3x3 array after the convex mirror, and this is a top-down view of the simple testing system. This shows a 5 points array. Here the points to show that although the points are designed to be the same size and the same energy, but if the point is further away from the zeroth order, which means the steering angle is large, and the diffraction efficiency will be slightly smaller. This is consistent with our previous grating test results. Here's a CGH that is loaded to the device, and this is the point array after the convex mirror. So once we understand about the device, how device works, then we start to build up a system for the LiDAR purpose. So here we use a laser diode, which we talked about earlier. Because it's diverging, so we need a collimating lens to collimate the beam to have the power in the smaller directed range. We also use iris to control the size of the beam spot. Here we have 2 Fourier lenses, so we use 2 lenses instead of 1 to have a much shorter focal length. The neutral density filter is here mainly for imaging purpose because the laser can be quite bright for the camera. We used 2 approaches. One is Fresnel hologram. This means you don't need a physical lens. You don't need a Fourier lens to focus to see the pattern, diffraction pattern in the far field. The lens function is integrated in the CGH, in the hologram. But as you can see, the points in focus is not very small and they're not very well separated. This is not good for the LiDAR, especially at quite long distances. Although you can reduce beam size with a lens of different focal lengths, but it's still quite spread out. So this is not very effective. Another approach is to use a Fourier hologram followed by a physical lens. Here we use 150 millimeter lens, and the horizontal field of view is about 10. This can be redesigned. It's just a figure at this moment. So as we can see that the diffraction pattern at where the convex mirror is quite bright, and the beam size is very small. After the convex lens, the spot size of the laser is also quite small. This is at when we change the target to different distance from the convex lens. We work out if we move the target to about 100 meters away, then the spot size would be about 300 centimeters. It's still too big, so we've reduced the lens, focal length to about 80. The same experiment is done, then we are actually able to reduce the spot size at 100 meters away to about 67 centimeters. This is corresponds to 0.4 degree angular resolution. This is very close to the top of the range, which is about 0.2 degree angular resolution. So a few tricks is played here to reduce that size, including moving the collimating lens and reduce iris size. So we can get the spot to a very small size to satisfy a top of the range system. Previously, we demonstrated locally a small field of view. Here, I've done the simulation for the full 360 field of view. This is where the convex mirror is. So beams are shooting towards the convex mirror and being reflected to the front and the back of the car, if you like. This is a top-down view showing the rounded convex lens and showing the spots where it hits the mirror, the convex mirror, not the lens. This is a test target to be calculated. So the hologram is calculated based on this image. And this is the experimental diffraction pattern in front of the mirror. We can see the pattern matches pretty nicely. However, you do see that there's a minus 1 diffraction order, which is present, has a low power, but still present. This is to be further optimized. This image is captured by one camera looking at focus on the laser spot shooting towards the front of the car. This is the same image shooting to the front of the car, just with the lighting off. So we're only looking at the 905 nanometer laser. On the top here is a diffuser, and the camera captures the spots on the diffuser shooting towards the back of the car. That's blurred because currently camera is focusing on the test target. But once we put the spots in focus, we can see the spots are quite small, or sort of similar size to those shooting to the front. So this is to demonstrate that we can design the CGH to have the laser spots at the desired location. So to design that to be wherever we want and to have a reconfigurable field of view. Here are some design considerations. As we know that in autonomous driving, there are a lot of sensors, cameras. For example, LiDAR is shown in this dark gray color. It's looking forward with not a very wide field of view. Other sensors like surrounding view with a camera, back view with a camera, and some blind spot with a range radar. So it's a system with a different type of sensors. Although people say, oh, we need 360 degree, but it doesn't mean we have to see all 360 just with LiDAR. So bear that in mind. So we, in order to design a good LiDAR corresponding to a driving scenario, we need to have good quality lasers, first of all. we have laser diode with good collimated lens integrated. As a result, show that a good lens can optimize the laser spot. So we have a small laser spot for a minimum angular resolution. Also, we can effectively use the laser power, so we don't waste the light. Also, we need LCoS spatial light modulator optimized for the wavelengths in use. So in that case, we have more efficient. We have more efficient. We have the lights point towards the part we want, and we would have a switching time, a good short switching time for the video rate. With such LCoS, we can actually integrate a number of lasers, not just one. Previously, we've only shown one. We can integrate 21 lasers, for example, each one having a 2 millimeter diameter spot. And each laser could produce 144 points, depends on the range and a few other factors. And for example, on one plane, the lasers can be arranged in such a case. So it's sending the laser light at an angle, and the LCoS reflect the light towards the center of part, which does not overlap with the mirrors here. So with such a system, 60 by 20 field of view can be sufficient. Other field of view can be used, can be on demand. So we don't actually need to look at the full 360 all the time. Most of the time, our eyes, when we drive, our eyes are facing forward. And when we turn the angle of the view also. At that time, the LCoS can steer laser beam towards a turning direction and be quite clever about it. So we have a smart LiDAR system. To conclude, I've shown that LCoS is configured for 2 wavelengths. It shows good device performance in terms of reflection and diffraction. It shows the reconfigurable points array can be achieved with CGH design. And it shows the laser quality is very important for such a system. System is designed with a 360 field of view. And we also talk about the LiDAR design requirements and considerations and its application scenario. Further works are required, especially on the detection part. This talk does not cover, but this is very important, how we detect the laser, how we calculate the distance, and where it's coming from. This is a proposed concept that we also use a convex mirror to collect the beam from all 360, and we use a detector matrix and some algorithm to work out the distance of the object. So both detection and algorithm needs to be explored. Of course, the transmitting part can still be further optimized for the best laser spot, for the best efficiency. That will be all. So thanks very, very much for your attention. And if you have questions, please contact me or contact our admin, Denisa. Thanks very much.